Today we're going to be talking about connecting your PLC. As you think back to MEC232, I provided you with this little trainer using the MEC232 series PLC, and it was already all wired. We didn't handle any of the connections. It was just already set up for you with a few inputs, a couple outputs, USB connection, and the power supply built into the little I/O box. So that was great for us as we were getting started, kind of removing the complexity of figuring out how do you work with it on a hardware level. Our idea in MEC232 is just getting used to a PLC, learning how to connect to it communication-wise, write basic programs, understand ladder logic, upload and download, the real fundamentals of a basic PLC program. But now in MEC232, we're going further into it. So now we want you to not just be able to work with existing inputs and outputs or wiring connections, but either add ones or troubleshoot ones that pre-exist your involvement with the PLC. So let's talk about the kind of minimum set of connections you need for a PLC. The first one's pretty obvious, is power. It has to have some source of power. There are a very few types of PLCs that have internal batteries that they might run off of, but those are really unusual to be in actual use. Typically, they will be powered by a permanent either 24 volt DC supply or a 120 volt AC supply. And this little one that we used last term is powered by 24 volt DC. So the power terminal input up here uses a wall transformer, takes the 120 volts out of the wall and rectifies it to DC and transforms it down to 24 volts. So all that was done pretty seamlessly and invisibly for this little trainer. If we look at the trainer we're going to use for this course, it's the next kind of family up. So it's still a Micro 800 series, but this is a Micro 850. And if you look at it, a little hard to see right here at this scale, but when you have your own one, you'll be able to see better. These left two terminals on the bottom terminal block are labeled plus DC24 and minus DC24. So we need to get at least, to power it up, at a minimum, we're going to have to connect two wires to the PLC to get 24 volt DC to these. And since at your house you're unlikely to have a 24 volt DC power supply around, we're going to use this little guy, which is, as you can tell, it just clicks right in there. It's designed to work with these 800 series PLCs. So it takes 120 volts in on the top. You can see there's line, or our hot, of the 120 volt supply. Neutral, that's the grounded current carrying conductor. Remember, that's different than a grounding conductor, which is this third one here. So this grounding conductor, just kind of refreshing back to MEC131, a ground is a safety device or a safety process for wiring that provides a path so that if any live voltage accidentally gets in contact with a conducting piece of the equipment, it should be safely shunted to ground and blow a circuit breaker or a fuse or whatnot. The neutral is often called grounded conductor, which can be confusing until you understand the distinction between grounded and grounding. So this neutral conductor is allowed to carry current in normal operation. The grounding conductor should never have current on it in a normal situation. The neutral is one leg of the single phase that we're using. Why it's called grounded is that back at the distribution panel, the neutral leg is tied to ground. That's the one place back in the panel where that's okay to do. As opposed to the line, it's kept separate all the way from power entrance to the building, goes through circuit breakers, comes out to your device, and then you can think of it going back, current going back on the neutral leg. Although, as you remember, for an AC circuit, power is alternating back and forth, 60 times a second, which direction it's actually going. Okay, all that kind of review the 120 volt input to the power supply. On the bottom side down here, you can see it's labeled, it's got a 24 volt DC output and it's 1.6 amps. There's two terminals for both positive and negative. There's no difference between either of the positive terminals. It's just to make it easier for you to connect multiple wires to the power supply. Okay, so let's just think a little bit more about what's happening in this power supply here. We said it's 120 volts AC. So you think about AC again as alternating current. The voltage is doing something like it is a sine wave. If this is voltage on this axis and this is time going this way, 0 volts is kind of right through the middle of the sine wave, and the voltage is always going up and then down below. So current, you could think about, is going backwards and forwards, the way the electrons are actually flowing through the circuit. So they're alternating, moving forward, then backwards, forward for a 60th of a second, backwards, etc. That's alternating current, the input to this. Then we have direct current coming out. So what that means is inside this device, it has taken this alternating current and done what we called rectifying it, which what that involves, just kind of out of interest, is it takes this bottom half of the wave and flips it over so that you end up with a wave something like that, and get rid of the bottom half. That's the first step of rectification. That's done usually with diodes in a bridge format. And then it uses capacitors and inductors to even out this bumpy wave to get it to where you have eventually a well-regulated power supply will just have a steady DC voltage. So in this case, the voltage is not changing over time. Current is always flowing in one direction in a circuit. So that's just our quick review of AC-DC. So we have AC in, DC out, and we need a DC supply to our power supply here. So that's a good match here for what we're needing to do. So we've talked about our first kind of most minimum connection, and that would be power to the device. So in this case, it's pretty easy to tell with looking at the actual device what power supply it needed. We said it was a DC 24 volts. Sometimes that might not be so clear, especially if it's already wired into a panel and you can't see very clearly what the labels are saying, or if it's in a dirty environment, the labels have all gotten obscured, or even in a chemical environment and the labels have been etched away or whatnot. Let's talk about how we would find out the specific requirements for power or other wiring that we might need to find out on a piece of hardware. So if you think back to last term when we were researching things for our different Allen Bradley or Rockwell products, we used the literature library. So let's pull up a website and go to the literature library. Okay, so the part number for this processor that we're using is the 2080. That just says it's a Micro 800 series. And then an LC50, that tells you that it's in the 850 series. And then we're using a 24QBB. We've talked about those part numbers before, what those different numbers represent. So we won't go over that again, but typing those in, I'm going to get a bunch of different literature options, and I want to look at the user manual. So there's installation instructions. While we're here, I'm going to go ahead and download that one as well, just so I have a copy of that open. We might need that in a little while. We can scroll down, see if the user's manual is one of the early ones here. Selection guide. Okay, so here's a user's manual, so I will just open that one. And what we were coming here for is we're starting to wire our PLC. So I'm going to look at the table of contents and try to figure out what section in this document I'm most likely to find information. And just based on experience, that's likely going to be in the specifications area or hardware features, or sometimes there's a section called wiring your controller. So let's just kind of scroll down to the table of contents. Again, before I get to the table of contents, just a reminder that in most of these user manuals, near the beginning of the manual, there's an additional resources. So this is a great document to start with because it has this link to many of the other documents you might need. So in this case, our PLC we're looking at has a plug-in module on the front of it. So it might also be helpful to look at the user manual for the plug-in modules if I'm wiring it up for the first time. So you can see a whole list of different instructions, installation guides, user manuals that might be helpful to us as we're working. Okay, but I'm gonna get to the table of contents. Okay, so here I said one of the places I might look would be in the hardware overview, hardware features. That might be a place to look. About your controller. That's okay. Power considerations. That sounds like something that could be useful for us. That's going to talk about different considerations when we're choosing a power source. And I said I wanted to look for the specifications. Might be a good place to find out exactly the power requirements. So if I go, specifications are usually at the very end of the document. Yeah, so that's right there. So we're using a Micro 850. So here's Micro 850, and it's a 24-point controller. So just to start with, I'm going to skip there, because anytime I'm looking up a hardware spec, that's usually my first spot I look. Okay, so I said, looking across the top here, there's a lot of different options. Let me zoom in just a little in case it makes it easier for you to see. Let's expand this. Oh, sorry about that. Not sure what the mouse did there. Try that again. Okay, 24-point controller specification. So here we are. Power supply voltage range. So it looks like all of this series of controllers all require a what we would call a nominal 24 volt DC power supply. There isn't a 120 volt AC option or a 240 volt AC option. They're all requiring 24 volt DC. So if you had something else like we do with 120 volt AC on our wall, we have to use a separate power supply to bring it down to the 24 volts. There will be some controllers that can use 120 volt AC as their power supply, but this isn't one of them. Okay, other things to consider on the power supply. We said, if you remember back looking at the front of our little 24 volt supply, it said it could supply 1.6 amps. So I'm going to look in here and see power consumption to see if that supply is large enough. And I'm just looking at simplistically right now. As you can see, there's two different ratings here. One is an 8 watt rating without plug-in modules and expansion I/O modules. So right now we don't have any expansion that we're using. We do have one plug-in module. So we might want to go take a look at the user's manual for that plug-in module to see how much the particular module we're using requires. But as a rule of thumb, you can see worst case scenario, if we had everything, all the plug-in modules and expansion modules installed, it would draw 28 watts. So if you think back to what it said on the front, it said 1.6 amps and 24 volts. So we have volts and amps, but the PLC's consumption is rated in watts. So hopefully you remember our Ohm's law. If we go back to look at this, remember that the Ohm's law is our relationship between voltage, current, and resistance. So basically the resistance would be the load of this device, the processor itself. At a certain voltage, 24 volts, it's going to draw a certain current. But they're not telling us what that current is. They're telling us what the wattage is. And we want to know the current because that's what we have here as an output rating. So we use the power law, which if you remember, power is equal to the voltage times the current. So in this case we have 24 volts times 1.6 amps. So you can already see we're going to be fine because it said at most it draws 28 watts and we're at 24 times 1.6. So let's just figure out what exactly that is. 24 times 1.6 amps, and that's 38.4 watts is the rated supply. And so looking back at our manual, we said we're going to be somewhere in the range between 8 and 28 watts, which is great. So we're going to have plenty of power for this, which is good because we're also using this same power supply to supply some other stuff in the trainer. And sometimes that's the case in an actual control panel. Most of the time it would be a dedicated supply that is supplying the processor itself and its I/O. Usually you don't share your power supplies on a larger scale than that. In this case we will, since it's a small little trainer, but that's just kind of a general best practice. Okay, so we've talked about the power supply. We can see that it needs between 20.4 and 26.4 volts, and that's just giving us some room so that if our power supply falls a little below 24, or there's a bit of a surge and it rises about a bit above 24, we're okay. If you look at that, it looks like they're saying about 2.4 volts above and about 3.6 volts below 24 volt nominal, and we'd still be fine. So that's a quick way to find out our power supply requirements. Anytime you have a new processor, I would encourage you to check the specification section before you connect it to power. We can also go back up and look real quick at that section where it was talking about wiring your controllers and hardware features. This just verifies where the different types of connections are. We'll talk more about some of the other connections here in a few minutes. So that's an overview of where things are located. And then I think there was one about wiring your controller. So let's go take a look at that. Install your controller. So under install your controller, that's talking about the mechanical installation, which you'll be doing next week. And then wiring it. So we'll just start looking at that section. Looks like it's about 10 pages. We'll just scroll through what's going on in there. And I would encourage you to read this, not encourage, I would ask you to please read this section over the next week. The wiring your controller section. It's talking about wire sizes here, giving you advice on how to route your wiring. You typically don't want your power wiring crossing your signal wiring. And if you do have to cross them, it should be perpendicular so that the wires don't act through inductive coupling, so that your current flowing through your power wire doesn't induce a signal onto your inputs or outputs to other devices. Just like last term where we looked up wire sizes for the Micro 810, this tells you what size wire minimum and maximum the contacts or input terminals are rated for. Talks about surge suppressors specifically on outputs, and we'll talk about this more when we connect relays up to it. But you can remember that when the magnetic field created around the coil of a relay solenoid shuts off, it can create a large spike of voltage as that field collapses, and we have to have a way to safely dissipate that without it getting spiked back into our PLC itself. So this section is just showing you how to do that using either surge suppressors for AC loads, or a diode can be used in a DC circuit. And there's different types, they're showing you that, and they then sell them as well, so information on purchase them. A good section about grounding, and then this is the terminal blocks that we'll talk about a little bit more later on, about what the actual individual terminals on each of the inputs and output blocks do for each model number. And we'll look at some diagrams like these later today as we're talking about syncing and sourcing. So I think that's a good overview of the literature review for now. So your first part of your assignment today that you're going to need to turn in is to practice using the literature to go find out what the input power requirements, so the power supply to power the processor. I'm not talking about the inputs like the input 1, input 2, input 3. I'm talking about the power input requirements for a 2080 LC10. So this is back to the little micro PLC series. That's LC10-12AWA. So I want to know what voltage does it require. for power. And your answer, I want to know what voltage it is. Is it voltage AC? Is it AC or DC? I want the publication number that you used to find it and the page number within that where you found that information. So find those three pieces of information and write them down. You're going to turn those in later as part of the assignment for today. Okay, so now we have hopefully a basic understanding of connecting power supplies to the PLC, or at least finding the information on what type of supply it would require. Next week in class we'll go over actually doing that physically. Let's talk about the other minimum connections we need to be successful using the PLC. We're going to have to communicate with the PLC, right? We're going to have some way of sending a program to it and then monitoring that program. So on this MEC232, we have a number of communication options available to us. So I'm going to try to get these covers off gently without breaking them, hopefully. Okay, so those covers opened up a number of communication options you can see here. So on the top we have Ethernet that you're familiar with, no doubt. We call that connection, the physical connection there is called an RJ45. It's a locking tab, and with it not powered up and connected right now, it's hard to see, but there are two LEDs there that show when it's connected, show whether it's connected to a switch and whether data is passing. So that's Ethernet. That's a high-speed networking connection. We can use it either to send data to the processor when we're downloading programs or uploading programs or whatnot. We can also use it to communicate with other industrial devices like HMI screens, drives, that kind of thing. The next one down here is a serial programming port. And this one, I'd have to look at the specs. I think it can do what's called RS-232. That's kind of the most basic version of serial. That's common. I take that back. That used to be common way for peripheral devices to talk to a computer. In serial, what serial means, we talked about this before, but just to review, serial is when it sends out information, one bit of information at a time in a string, as opposed to parallel, where you send out multiple bits at one time over a bunch of different inputs. So this is a serial device, and so RS-232 was one of the early serial protocols. Right below it, we have what's called a USB port, right? And that stands for Universal Serial Bus, if I remember correctly. So this is a more modern serial device. This operates at much higher speed than this older standard here. But the RS-232, this one can also do, I think, RS-422 or 485, which are a little different. Instead of RS-232 is just from one point to another. So it can talk from the PLC to your computer or from the PLC to an HMI. It's just, point to point. RS-485 can be a string network of multiple devices on one connection, kind of more like Ethernet, but in a different format of how it does it, a much more rudimentary way of passing data, much slower. So serial that can do longer distances but slower speeds than USB, which is very much plug and play, easy to use, but it's only used for programming the device or getting information in and out of the device. It's not used for any industrial processes, whereas either the Ethernet or the serial port here can be used for I/O, well, not I/O in these cases, but in communication with other automation devices. Then lastly, under the cover down here, you'll see now that we've moved to the 850 series as opposed to 810, we have an actual hardware, what we call run program mode switch. So when it's in the middle position, I'm sure it's hard to read right now, but that says REM in the middle, and that means remote. So when the switch is in the middle position, the remote position, That means you can set whether the processor is in the run mode, where it's executing its program, scanning through inputs, making logic decisions, and then setting its outputs. That's our run mode. Or if it's in program mode, where it's not actually monitoring its inputs or setting its outputs or running the program. It's just ready for you to send a new program to it, troubleshoot it, get information out of it. So in the remote mode, that decision of whether you're in run or program is done by the computer it's connected to. If you turn the hardware switch to run, now this device will always be in the run mode whether you try to change it with the computer or not. You can't change its mode with the computer. Same if you turn it all the way to the right into hardware program mode, it's only going to be in program mode. You can't change it from the PC. So I think that makes sense what's going on there. So that's kind of the overview of our communication options and the mode switch on the PLC. Just to review, we've got Ethernet, we've got serial, and we've got USB. So for the next phase of your assignment today, the next part that I want you to practice is look up for this part number. This is going to be a different series. So a 2080 LC20. So that's an 820 series instead of an 810. And then let's do 20 QWB. I would like you to go find out for me what communication options are built into that. So just to review, for the 850 we just looked at, it had Ethernet, it had serial, often called RS422 or 485, and it had USB. I want you to go look and see which of those three, all of them, none of them, one of them, etc., which of those this model number has. And again, I would always start at the user manual, and if you can't find it in there, use the additional resources section at the beginning of the user manual to browse for documents that you might have that information in it. But my guess is that for all of these pieces here, you'd be able to find that in the user's manual. If you think back to, there's a hardware features section or hardware overview that shows you the locations of the different connections on the device itself. That's a good way to look for communication ports. There's also a communications section usually that talks to you about how do you wire up your RS422 or 485, or how do you configure your Ethernet port, that kind of thing. So go do some literature research and find out these pieces of information about the LC20 20QWB. Okay, so we've talked about wiring the power source for the PLC. You should be good on that. We talked about the communications. Some of those you may need to wire. RS422 or 485 are often actual screw terminals on the processor itself. USB or Ethernet, there's not much to those, right? You just plug a preformed cable in for those. What else will we need to use our PLC? Well, I think it's pretty obvious that off the top of your head, we're going to need inputs and outputs, right? PLC doesn't do much good if it's not actually interacting with the machine, the process, the environment, whatever it is. So we'll start with outputs, because in theory, I suppose you could have a program that had no actual hardwired inputs. It was all based on timers or Ethernet information coming from other locations. But it would be unusual to have at least a micro series processor that didn't have any I/O, or specifically outputs, connected locally. So let's talk about outputs first. I'm going to put a couple different 800 series processors up here on the camera. So you can see this is a Micro 820 series, similar to the part number I just had you look up communication options for. And hopefully you were able to figure out what options were available. I'm not going to answer that here, but in looking around on it, you might see something related to that. But what I am pointing out is that the general layout on these controllers is that the bottom removable terminal block, and actually on the 820 they're not removable, but the bottom terminal block are the outputs. If I roll it up here a little bit, You can see the labels there of commons and outputs labeled O, 0, 1, 0, 0, etc. And on the top are where our inputs come in. That's the general layout on these devices. Okay, so that's an 820 series. You saw the 850 that was unwired. Here's an 850 that has some outputs connected. You can see down here, those first two we talked about are the power supply connections from our external power supply. And then there's a number of outputs that I'm using in this case to control inputs on a stepper drive. And I'm glad I happen to have this here when we talk about connecting outputs and inputs of different styles of syncing and sourcing or whatnot. This is a good example of where you're doing that. Here I'm using the output from the PLC as inputs to the stepper motor drive. So for example, there's an enable output, an output from the PLC that's an input to the stepper drive saying when I turn this bit on, I want the motor driver to be enabled. And you can see it's enabled right now. I can't turn the motor shaft at all. Whereas if I turn the processor off, or actually depower it, which I'm not going to do right now, then the drive would no longer be enabled. Other ones on here, I believe I'm sending pulse and direction as well. And we'll talk more about those when we talk about motion control. But that's just showing you how the outputs can be connected on the bottom. So let's talk about types of outputs. If you think back to our Micro 810 series that we used here, again, the outputs are on the bottom. There were just 4 outputs on this one. And if you remember, when you would turn the PLC outputs on or off, you would hear a click because these outputs are relay outputs. So there's actual little micro relays inside the device that are turning on and off to control these contacts. So in this case, those outputs are what we would call, well, first off, these are discrete outputs, right? They're either on or off. They're digital, discrete, binary, whatever you want to call it. There's no in-between state. You can't set this output to be 7. It's either on or off. And in this case, it's what we call a contact output. So it's not outputting a voltage. So this device is powered by 24 volts. But when you turn on output 0, 0 in your ladder logic, you're not putting 24 volts on this terminal. What you're doing is connecting between common and 0, just like a switch or a relay contact that we would have used when we were doing discrete control devices, right? So if you think back to a relay, right, has a solenoid coil, and the armature of that is connected basically to a switch. So if you think about it, it's an electromagnetically switch that if you create a voltage across the coil, it's going to suck the switch up and connect the common to, so if we're saying it's energized and it's connected, that would be to this terminal. We would call that would have been the normally open. So when it's de-energized, this would then come down to this state, and this is called the normally closed terminal. That would be if we had a standalone relay on its own. We would call this single pole, double throw, right? It can be, there's 2 different potential paths. It can either connect from common to normally open or common to normally closed. The relay inside here is a single pole, single throw. So it only has a common and a normally open. So it doesn't have this terminal here. It's just either connecting common to our terminal 0, 0, or they're disconnected. So it's basically just like a mechanical switch. So in some ways that's nice in that they're very simple to work with. If you just hook up a voltage source on this side, if you just hook 24 volts to the common, come out you're normally open, and say you wanted to run an LED, that's our symbol for an LED lamp, and then this went to our minus. Anytime you energized output 0, it would connect the common to normally open and your LED would turn on. So it's useful in that it can use any different voltage. This could be 24 volts, this could be 12 volts. It's also useful in that if you look at these 4 outputs on our relay based, they each have their own common. So I could hook up a DC 24 volt to this common to run a 24 volt DC lamp. I could hook up a 5 volt DC to this common so that when I connected it to output 1, it would work with a 5 volt device. And I could connect 120 volts AC to common 2, and then when I connected it to output O2 using my ladder logic, then I'd be switching 120 volts. So the limitations of what you can run through those relay contacts is again something we can find in the user manual for the device. So let's take a look at that. Let's see if I have the 810 user manual open. This is 820 user manual. There's an 810 user manual. So I want to look at, I'm just going to go to specifications again. And this was a QWB, so that's this model right here. And we got 4 outputs. Let's see if it talks about our output ratings. So there's AC inputs, DC inputs, analog inputs, DC outputs, relay outputs. Okay, so here's what I'm looking for. So for relays 0 and 1, it looks like, so the first 2 outputs are rated up to 8 amps at 240 volts AC, or 5 amps at 24 volt DC. And outputs 2 and 3 have about half that capacity, so they're rated for 4 amps at 240 volts AC, or 2 amps at 24 volt DC. So that tells me what they're designed to switch. Anything up to 240 volts AC, as long as it's less than 4 amps or 8 amps on the first 2 inputs. Also talks about minimum voltage for switching. And down here, one thing that's useful is the relay output life. So there's 10 million cycles is what they estimate the life of a relay output at. Electric, that's mechanically just how long the physical connection between the solenoid and the switch terminals. Electrical rating with at load, so if you're at full load, it's not actually going to get to whatever it is. Now it looks like it's 10 million cycles. They're saying if you're actually switching that full 8 amps at 250 volts, you're probably only going to get 50,000 cycles out of it. So this here is showing how you can figure out, okay, if I'm not actually at my full load 8 amps, how many cycles would I get? In this case, it looks like you could get up to, these are in 10,000, or in 1,000, so 500,000 cycles if you're at minimal load. Okay, so there's different charts for the first 2 inputs compared to the second 2 inputs. I think that's a good overview of our relay outputs. So again, relay outputs, kind of very simple, very basic. Advantages, you can work with different voltages with the same controller. You'll see when we get into like transistor outputs, they're set for usually a specific range, like 24 volt DC or 12 volt DC or 120 volt AC. It's not where you can use the same set for multiple voltages. The other thing that's unique here is that each output has its own common. That comes back to, that's partly why we can use independent voltage sources. When we get to DC or AC outputs, that's not the case. They'll start sharing commons in groups. Okay, let's pause there to think about relay outputs. Make sure you're comfortable with why we use relay outputs. Simple to use. On the downside though, they do wear out over time. And the other thing, since they are a mechanical device, they can only turn on and off so fast. If you're trying to send out a series of fast pulses to a stepper motor driver, a relay is not going to be a good choice for that. We said could be only as many as 50,000 cycles at load. So if you're turning something on and off every a couple times a second, that's quickly going to reach the end of lifespan of those mechanical contacts. So when we're looking at switching more quickly, and longer lifespan, that's when we're going to look at something other than a relay contact. So let's talk about what options do we have besides relays for our outputs. Okay, so relay outputs, simple, multiple voltage flexibility, but limited lifespan and limited speed they can turn on and off. That's relays. Our next simplest, so moving up in level of complexity of connections, would be AC outputs. So in an AC output, we are going to have a terminal, a common terminal, but we're not going to have an individual common for every output. We're probably going to share them in groups. It may be one group per output card. It may be one common per 4 outputs, per 3 outputs. We're not going to have an individual common for every output. And that has to do with the internal circuitry and just the number of terminals available. If you think back on the Micro 810 that we were just looking at with relays, it only had 4 outputs, so it didn't take up a lot of space to have both a common and a signal, the output, for every output. That was a total of 8 wires for our 4 outputs, right? When you get into higher density cards, like in compact logics or whatnots, you can have up to 32 inputs or outputs per card. If you had an individual common for every output or input, that would be 64 wires on a single card, and that can be really hard to connect up. So they will group them into usually a minimum size of 4, sometimes groups of 2 if they're small expansion cards or whatnot, but groups of 4, 8, 16, etc., where they'll share a common. So you'll have a common, and then you'll have your actual output. So let's look up a wiring diagram for a PLC that has AC outputs, and look at the actual wiring diagram for that. So I've pulled up the installation instructions for a compact logic AC output card just for us to walk through and take a look at the wiring diagram for an AC output, to talk about the commons that I just mentioned and just how an AC output would be wired. So looking at the table of contents here, let's go to field wiring connections, and here you can see an idea of how we would connect it. So looking at it, it looks like we have one common, that's in this case they're calling that VAC1, that is shared between these 8 outputs, 0 through 7. So in this case, we could have a 120 volt supply out to these 8 outputs. If we had another need to also switch, say, a 240 volt AC outputs, we could do those down on this lower group, but we couldn't share in the upper. So when output 1 turns on, it has to be turning on the same voltage as if output 0 or output 3 were turning on. All of these are going to be using the same power source. So it's not like relays where we could have 12 volts on output 1, 36 volts on output 3, 120 volts on output 5. Now, whatever source we're using, it's going to be the same for each of these 7 or 8 outputs. That source can be anywhere between 100 and 240 volts AC, but it's got to be the same for all of them. And again, the reason we do this is that it saves us, in this case, 7 wires. If we had an individual commons for every output, it would take 8 output signals and 8 commons. And so in this case, we only have 1 common for those 8. And then, so it's a 16-point card with 2 commons. So in this case, they're grouped into groups of 8. So hopefully that makes sense about commons and AC outputs. So they're a little more complicated than just relays, but a little less complicated than DC outputs. So let's talk about DC outputs now. I guess one other thing about AC, the actual switching device in an AC output is usually what's called a triac. So a triac is a form of transistor, basically switching device that can handle current going in both directions. So if we remember again that if we look at, let's say we had this card that we're talking about here, and these are control relay coils, looks like they're using. When we turned on output 1, current would be going for a 60th of a second. It would be going from line 1 through the common, through the triac, that's the actual switch inside the PLC that we control via ladder logic, and then it would come out through the control relay, our actual load, and go out line 2. So for that 1/60th of a second, it's going line 1, in through the common, through the triac, out through the relay coil, into line 2. Then it's going to reverse, and current's going to flow back the other direction for 60th of a second, as long as that output remains on. So it's basically an electrical switch connecting the common to the output. That's what the function is there. And the device that's doing that is a triac fancy transistor that lets current flow both directions when it's turned on. That's different than a DC output. So let's talk about how DC outputs work now. And before we get too far into the details of that, let's think about what's required for a DC circuit. So for a DC circuit, you're going to have some DC supply. In our case, most of the time in this class, it'll be a 24-volt supply. Because the outputs of the PLC have to have some voltage source that you're supplying to them. They don't just create energy out of nowhere. You have to provide a 24-volt source to the outputs that is separate from the actual supply to the processor. So we have our 24-volt supply, and it's an output. So in this case, the PLC is going to provide control of this circuit, and then we're going to have a load too. So we're going to have PLC output, and then we'll have a load. Those are the two things that we'll need to complete the output circuit. We have a power source, we have the wires, and then we have the PLC output that's going to switch the power source to control the load. So in this case, in an AC circuit, that was really easy to do. If it was AC, the current would be bouncing back and forth, so we had to use a PLC output that had a triac in it, so it would let the current just alternate back and forth. Now with DC, it's a little different. The current is always going to be going this direction if we go following conventional current flow theory. So the current is always going that way. So if that were the case here, the PLC switching on and off here is going to be providing a positive voltage to the load when it's turned on. So this load could be a control relay coil like it was for the AC. So in this case, when we turned on via ladder logic our PLC, and just call this output 00, if we turn on our DC output 00, it's going to connect our positive 24 volts to the positive of the load, and current will flow through the circuit. And in that case, we call this PLC output a sourcing output. It is a source of current flow. Current is providing a positive current flow, positive voltage to the load. That's a sourcing output. In that case, the load here is always tied to ground. It always has that connection to ground, right? The PLC is switching on and off the load's connection to power. We could do that an opposite way if you think about it. We could have the same 24-volt supply, and instead of having the PLC first, we could have the load first if we had our control relay coil, and then we could have our PLC output 00 again. In this case, the load always has a connection to the positive side, and the PLC is connecting or disconnecting the negative side. And in this case, the PLC is what's called a sinking output. So, and when we get into inputs, it'll be more common, but they're in pairs, kind of. If it's a syncing output, that means the load is being sourced. If it's a sourcing output, the load is syncing. The load has always got a ground or the negative tied to it. And if the load is syncing, the load has ground all the time, and the PLC provides the source. If the PLC is syncing, then the load, our coil, always is connected to positive, and we're switching off and on the negative supply. That's syncing. So let's go back and look at one of our user manuals to see an example of syncing and sourcing concepts. So this is our Micro 810, the little one we started out with. Let's take a look at the output wiring diagrams for it. So the version we were using used relays, but there are versions that use DC outputs as well. So let's go down and look at those. Controller I/O wiring, page 21. Here are the actual terminal blocks. So let's look at one that is DC outputs. So that's this one here, a 12 QBB. Let me zoom in a little more. 12 QBB. You can see the outputs. Looks like we have 1, 2, 3, 4 commons. So in this one, where they're dense enough, they have a lot of commons, because again, there's only 4 outputs. When we look at one like our 850 that we'll look at in a little while, you'll see that the commons are not independent like that. Okay, so scrolling down though to look at the actual wiring, here's an example of a syncing output. So this is, let's go back. So in a syncing output, we said that the PLC is switching on and off the ground for the device. If we're looking at this control relay example, the PLC either connects the output to ground or disconnects it from ground. Let's see how that compares to what our manual is showing. So here is our load. This would be our control relay. If we look at the two sides of the load, one side looks like is tied to positive all the time. That is also connected to the DC positive side of the output card. And then the actual individual output itself, this is the output that would get turned on if you address this output in your ladder logic. It is connected to the other side of the load. And what you can see what it's doing is switching through this transistor here the path to the common, to the negative power supply side. So when you turn on this output, it connects this side of the load device to the negative power supply. So the PLC is switching the negative side of the load. It's providing a sync to the current flow. Current is always ready to go through the load, but until the PLC provides a path to ground, it can't do it. So that's a syncing output. If we scroll down, we'll skip the input ones. Here's a sourcing output, and you'll see everything is just kind of reversed. Now, the positive is the common. You can think of it as far as each of these outputs would use the same positive power supply, and the load is tied to the negative all the time. You can see that. Negative supply always connected to the load, and the PLC switches the positive side. So when you turn on this output, it's connecting through this path right here to positive. You can see there's a diode here, so it's never going this direction. The only way for current to flow through the circuit would be from here, through the output, through the load, into the ground. So sourcing output means the PLC is switching on and off the positive supply to the output. Okay, let's look at one other example of that I pulled up. Here is some more outputs. Let's take a look and see if we can figure out if these outputs are syncing or sourcing. So we're looking at the output of a DC output. This is an 850 series, And you can see the outputs are grouped here. We have a common 0 that looks like it's an independent common for just output 0. And then output 1 also has its own common. You can see they're grouped by this line above, is showing this common is tied to this output. Then for outputs 2, 3, 4, and 5, there's a single common for those ones. Terminal 7 is the same common for all those 4 outputs, just like common 3 is the common output or the common terminal for outputs 6 through 9. So far we've seen that they're grouped in 1s for the first 2 output and then in groups of 4 for the last 8. But that doesn't tell us anything yet about whether we're syncing or sourcing those. And what's interesting here, it looks like these outputs must be able to be AC or DC if we looked up the specs. Because you can see on outputs 2 through 5, they're labeling the lines as L1, L2. So that's our notation for AC lines. So in that case, that means it's got a triac or some version of a transistor that can switch AC. Looking at the last 4 outputs here, we can see they have a DC supply. And this is, now we can, by thinking it through, we can figure out, is this a syncing or sourcing output? You can see that for each relay, they all are always tied to the negative of the DC supply. So that means the PLC is switching the positive supply, and you can see that's correct. The positive supply comes in on the common, and then each individual transistor connects that positive or disconnects it to its output. So if you turn on output 7 in logic, it's going to use a transistor to basically connect terminal 12 to 14. So voltage will flow in 12 through your transistor, out 14 through your load to ground. So I'm going to pause talking for a minute, and you tell me in your head, does that mean that's a syncing output from the PLC or a sourcing output? And it's a sourcing output, right? The PLC is providing the positive source for current flow in this case. So this is an example of sourcing. If instead this was the negative supply and this was positive, then it would be a syncing output. Okay, I think that's a basic introduction to DC outputs, both syncing and sourcing. Okay, so let's give you the next part of your assignment for today. And this one is 2 parts. First off, I want you to look up for this part number an LC50. Remember again, these are all 2080, saying it's micro 800. So an LC50-24 QVB. I want to know, is that AC outputs, relay outputs? If it's DC outputs, is it syncing or sourcing? So basically just tell me AC, DC, relay, how many outputs, and if they're DC, tell me if they're syncing or sourcing. That's the first part. For the second part, I want you to take your Micro 810 trainer that you have. It should look exactly like this, with the exception of I have an additional input wired on mine right now that you won't have on yours. But I want you to take what we've just talked about and tell me, you're going to write this down, I'll tell you how to tell me about it, but tell me on the outputs whether they're configured as syncing or sourcing. So they are using a relay. So it's not a DC transistor forcing us to syncing or sourcing, but you can think that the same concept still applies. Looking back at, where's that drawing? At this drawing here, whether it is a transistor doing the switching or a set of contacts, you can still have it physically arranged to be either syncing or sourcing, right? So this could be our just relay contacts in here. If we have a relay contact up here, then that's wired as if it was sourcing, even though it's using a relay contact. If instead the relay contact is switching the negative side of the output device, then it is a syncing arrangement. So in this case, our outputs are lamps, right? So we have a 24 volt source that is connected somewhere here. I'll talk more about that in a minute. And it comes up, and then we have a lamp. And what I'm asking you to tell me is, do you think the relay contacts are up here and the lamp is down here, if this is positive, negative? So is this the case? Then it's arranged as if it's sourcing. Or do you think the lamp comes first and then our relay contacts, in which case it's syncing? So you can't tell that without a multimeter or opening up the box, which I don't want you to do. So to give you a heads up on this, I'll let you know that this wire connected to common for each of them, if you look, you'll see all of the commons are tied to an orangish wire. That is the positive of the 24 volt supply. So the common of the relay contact is tied to the positive supply. So use that information, think that through, and decide if you think these outputs are configured as a sourcing or a syncing arrangement. That's the second part of this chunk of the assignment. Okay, so let's review what we've covered so far. We've talked about connecting power to supply the processor itself. We've talked about our communication options, and then we've covered 3 different styles of outputs. We had relay outputs, the most simple and easy to work with, but kind of the most restricted as far as speed and longevity. We talked about AC outputs, which can switch on and off much faster than relays and have a longer lifespan, but require a little complexity in that they share commons. So you can't have an individual source for every output. You have to group your outputs by the voltage they need. So you could control 4 120 volt control relays off of one group of outputs, but you would have to use a different group of outputs if you wanted to control a 24 volt AC output. And then we got into DC outputs, which were kind of the most complex thing we've talked about so far. So in DC outputs, we have syncing or sourcing. And just to review, syncing means the DC is switching the negative side of the power supply. Sourcing means the DC is switching the positive side of the power supply to the load. Okay, now let's go into inputs. So similar to inputs, we can have different styles. Inputs similar to outputs, we can have different styles, right? We can't have relay inputs. If you think about it, that doesn't really make sense. Relays can be outputs because they're switching whatever voltage you're providing. An input is you're looking to see is a voltage present or not. So it wouldn't make sense to have relay inputs. So we're going to have either AC or DC inputs. And again, AC inputs are simpler. I'm not even going to go open up a user manual for them because they're so basic. But again, they'll be grouped with a common. So an example would be you would have a common, and then you would have input 1, input 2, input 3, and input 4. And let's say for now we're going to just use simple inputs. So let's say we're using push buttons. So this would be the terminal block of our PLC. It has 5 connections for those 4 inputs. Let's say there are 4 different push buttons. What we would have is we would have our AC supply. So we would have line 1 of our AC supply and line 2. And this could be 24 volts AC, 120 volts AC, depends on the specifications for the card or the PLC. So what we're going to do is tie one of those lines to common. read the spec manual to see if it matters whether it's the neutral or the hot line. Often doesn't matter, but sometimes it does. So line 2, in this case, I'm tying to common, and then from line 1 I will have my 4 push buttons. I'm drawing them on their sides just to make it a little more compact. So when you push the push button connected to input 1 for a 60th of a second, current's going to be flowing in this direction, and then it's going to reverse back. And inside the PLC, instead of having a transistor that is switching, now we have a sensor that is watching is current flowing through this path. So it is flowing when I push the push button. Since this is normally open, it's only flowing when I push it. So when it senses that current is flowing through input 1 and out the common, then when you look at that input in your ladder logic, that would show as a true. Same thing if you press input 2 in this case. Current will flow from line 1 into the I2 through the second current sensing and out through L2. And then a 60th of a second later, it reverses and just goes back out. So there's no polarity, there's no positive or minus on the push buttons, etc. So that's pretty simple AC inputs. Okay, let's go on to DC inputs. So now we're back to the concept of syncing or sourcing. It's just now we're looking at inputs. So let's do a simple version again. Let's say we have a common, I'll just call it C, input 1, input 2, input 3, and input 4. So again, 4 inputs sharing one common. Let's have this represent our terminal block. And now we're going to have a DC supply. So let's start out by doing a positive and a negative. So let's say this is positive 24 volt DC and this is the negative 24 volt DC from our power supply. So now is where I have the choice, and just because of how I've drawn it here, to start out for this example, I'm going to connect the negative to my common, and then just like we did for AC, we can connect the individual, let's draw them as limit switches this time. Just for a little variety. Okay, so in these instances, I have drawn them as, if you think back, are those normally open or normally closed limit switches. And if you remember from our MEC233 or MEC233, if a limit switch is drawn with the bar above, and they're on their side here, so that's a little hard to tell, but you can always tell which side is which by the triangle shape below it. So these are normally closed, right? Gravity would hold the bar against the contacts until something raised the limit switch. But it doesn't matter, normally open or normally closed. You can have normally closed syncing or sourcing, normally open syncing or sourcing. That the normally open, normally closed doesn't affect whether it's syncing or sourcing. So in this case, it looks like the switches are all connected to the positive rail, and the PLC is providing the ground or the negative side of the DC rail. So hopefully that sounds like this would be a syncing input. The PLC is syncing the current, right? Positive current is flowing from the positive rail through the switch, and the PLC is providing a sync, right? It's providing the negative side. So current flows down through the sensing element and out through the common. So this is syncing. The same arrangement could happen if I just switch these here to this being the negative 24 volt DC and this being the positive 24 volt DC, now it's a sourcing input. Let's walk through the current flow in that real quick. So in this case, all of one side of the switches is connected to the negative, and then the positive is connected to the common. So in this case, the PLC is providing a positive supply to the input device, and when the input device is switching whether it goes to ground or not. So in this case, the PLC is the source of current. Current is flowing from the PLC to the input device. So this is sourcing. Okay, so we've covered DC inputs at a basic level now, both syncing and sourcing. And I'm sure you were wishing that I was going to say we're done, but unfortunately there's one more level of complexity to this that we're going to add in now. And that is that so far in my input examples I've used either a push button or a limit switch. And again, those are what we would call contact-based inputs, right? They are just providing a conductive path from a voltage source to the input terminal. They are not active powered devices. They don't require a power supply of their own. They are just connecting power to an input or connecting ground to an input. And that's a common input, right? Like, so a toggle switch here, this is an example of those type of contact closures, right? When I connect it one way, when I twist it one way, it connects this terminal and this terminal together. When I toggle it the other way, it's connecting that same common terminal with the other outside terminal. So that's a set of contacts. Again, non-powered device, just providing a conductive path. A push button, same idea, right? It has a common terminal. This one has a normally open and a normally closed push button. It's a set of mechanical contacts that are being connected in there. To see what's going on, I often use an example of relay contacts because they're easier to see. If you look right down here, you can see that when the armature pulls that middle path, that would be the common again. So this terminal right here, if you look at it, that would be labeled C. It comes up to the top of this arm, level arm, and then switches back and forth between this terminal and this terminal. So if you look at this diagram here, on a schematic it might look something like this. This one right here would be the common terminal, and then we're going to have this terminal right here. If you look, it is normally connected to the common unless the solenoid pulls it down. So this top one is the normally, it would be labeled, so this one's common, C. The top one would be the normally closed, and then the next one down you can see is the normally open. So in this case that would look something like and then the armature, the solenoid, the electromagnet basically, that's that piece right there. So it has, you know, a plus and a minus for the coil. So this again is just showing what physical contact type inputs. This could be used as an input to a PLC, switching an input on or off. Same thing's happening inside this push button and inside this toggle switch. Those are all the types of inputs we've dealt with in MEC231, also in MEC131, 133. We all use this type of contact pretty much. Except in 243, if you'll think back to 243, when we used the photo eye, you'll remember that it required its own power supply. So the connections to it had a power supply to power the actual sensor itself, and then instead of being just a conductive path for the output, it actually provided a voltage source, and that is really common. That's probably more common as a type of input than a push button or a toggle switch or whatnot. If you think about machines, most of the inputs of machines are monitoring positions in a machine, monitoring pressure, monitoring flow, all things that require some active process. So I have an example here of one of those types of sensors. This is an inductive proximity sensor. So what it does is it has electronics inside this case that are monitoring. It creates a small magnetic field around it, and if something magnetic, or not magnetic, but ferrous at least, something that affects magnetism comes into its field, it will turn on its input. So if you watch on the black body back here as I get this closer and closer, eventually a little red LED is going to turn on when I get within a certain range, and it depends on the orientation of the part, where I am on it, but you can see that LED turning on and off. And right now, that device is connected to the input of one of my PLCs over here. But if you're seeing that LED, that kind of gives you a heads up right away that this is a powered device. It's not just providing a connective path. So if we also look at this tag on the side of it here, you can kind of see. Let me come back down with my camera again. You can see that it is a 3-wire device. There is a brown wire, a black wire, and a blue wire. And looking at it, you can see that it requires a positive 10 to 30 volt DC on the brown wire. The blue wire is the negative of that supply, and then the black is the signal. So hopefully, if you're looking at this, you're starting to think through, okay, that little black box with the line through it, that's representing my PLC input. So this sensor device is a powered device. It's not a simple just contacts now. Now we're providing a voltage to the PLC, not just a conductive path. So now we need to think about, okay, is this a sourcing device, a syncing device, and what type of PLC input would I need? Because so far we've talked about just what the PLC's perspective was. So if we're looking back at this PLC input here, the way I have it drawn right now, the PLC is what this would be called a PLC sourcing input. You see that? Inputs that are, I want to call active or electronic inputs, where it's switching a voltage, the sensor itself is also either syncing or sourcing. So this is why I was saying we have one level of complexity left. Now we need to make sure that we're pairing our sourcing PLC input card with the right type of sensor. And they complement each other. If the PLC card is sourcing, that means the input device needs to be syncing. And I think that makes sense. If the PLC is providing a positive on the input, then the input device needs to be switching the negative. So it needs to basically, if the PLC is a sourcing output card, a PLC is a sourcing input card, then the input device needs to be a syncing type device. And you can look at that, even seeing that even with a non-active device, what this switch is doing, it's switching the ground. That sounds like syncing, right? So let's look at this device. Is this device providing a switched ground, or is it providing a switched positive? And remember that that box is representing our PLC input. So in this case, it's saying that the PLC input is always tied to negative. So, and that means that the sensor itself is switching the positive. So this is a sourcing sensor, so it would need to work with a syncing card. Does that make sense, I hope? So this proximity sensor that I have would not work appropriately with it being put in place of this limit switch. So the key idea is you have to match both the input device itself, in this case the proximity sensor, and the input card. And they always will be the opposite function. If one's syncing, the other is sourcing. Here's the biggest caveat of this whole thing that we're talking about today about inputs. And that is that, believe it or not, manufacturers are not standardized on how they label their cards as whether they're syncing or sourcing. And it comes down to what we just, the level of confusion we just added in. Some manufacturers describe their PLC input cards as syncing using the language that I've been doing, that the PLC itself is providing ground. Other manufacturers describe their cards as syncing if what they mean is that the actual input devices are syncing. So under Allen Bradley, since that's what we're using, I've been teaching you how they refer to their cards as sourcing. So they say a card is a sourcing input card if the comment is tied to positive and the device switches the ground. So they call that a sourcing card, because they're referring to their PLC card as the source. Some manufacturers with this exact same schematic would refer to the card as syncing because they're meaning you're using syncing inputs with it. So my biggest takeaway for this lesson is anytime you are connecting a DC input to for a PLC, and it's an active what I call an active input, a powered sensor, you need to have the schematic of the sensor and you need to have the user manual and schematic of the PLC card to make sure that you're connecting it using the correct schematic no matter what they call it. Whether they call it syncing or sourcing, that the current flow is correct. So you can see it's complicated, but it is important. This is one of the most difficult but also most common issues that people have when they're adding a sensor to a PLC. And I want to talk a little bit about where this comes from, because I'm using the terms syncing and sourcing because those are the common way of being described in industry, and they're the easiest way, I think, to learn it, with the idea that anything that is sourcing is providing a positive supply. Anything that's syncing is providing a ground or a negative path. But there is another terminology that they use in industry, and that is NPN or PNP. And that comes from the type of transistor that's being used inside the device. So again, just like we said, inside the output device or the output card of a PLC, there's a transistor that's switching the output on or off. The same thing is going on inside this little guy. So there's sensing circuitry that's monitoring the magnetic current, but then the actual device that is turning on or off, the black wire here, that's another transistor. And transistors can be either NPN or PNP, and the N's and P's stand for negative and positive. So an NPN transistor is made up of a sandwich of a negative semiconductor, positive, and then negative. So that's where it originally comes from. That's an NPN transistor. And just pretty obviously then, a PNP has a positive layer, a negative layer, and a positive layer. You don't need to know exactly what's going on at a semiconductor level. You don't even need to know generally what's going on at a semiconductor level. The main idea you need to know is that they behave in opposite fashions. So the symbol for a transistor is a way to tell between these which is which. And transistors are made up basically of back-to-back diodes. So an NPN transistor, the symbol for it shows, basically you can think of it as a diode heading out down the bottom, another line coming in, and then this is the base. So a circle with a triangle heading out, this would be an NPN transistor. And these are labeled, this arrow is always going out on the emitter, so this is the emitter terminal. This is the collector, and this is the base. Again, you're not going to be designing any circuits, but it is helpful to know what people are talking about, where these names come from. So in an NPN circuit, in general, you can think of it, NPN has the load is on the collector, and this would be a positive. I'm going to redraw this on another page so we have more room actually. Okay. Draw the symbol again. So NPN has arrow going out on the emitter, base. So this would be a super simple kind of circuit using a transistor. This is C, E, B for base, collector, and emitter. And if you were using this as a switching device, this would be the output. And let's use the example of this little inductive sensor. You would have a bunch more circuitry that I'm just going to draw as kind of a cloud over here. This is the circuitry that decides whether there is a inductive product, whether there's a ferrous metal piece out here. And if there is, it's going to create some small voltage. So you'll have some very small voltage change on the base. And what happens when you put a little bit of current going from the base to emitter in an NPN transistor, you can switch a lot of current going through the collector to emitter. So a transistor, we talked about this back in 131, transistor is just an electrical switch. It can turn on much faster than a relay. It can turn off. It doesn't wear out. They burn up if you flow through too much current through them, but they're very reliable as long as you don't exceed their capacity, and very, very fast on and off times. So in an NPN transistor, again, we'll put that, this is NPN, when you put a small amount of voltage on the base to create a small amount of current going out the emitter, that basically opens up the switch and allows a large amount of current to flow collector to emitter. So transistors can be used as amplifiers. So if you put in 1 milliamp or 1 microamp on the base, gain across these can be like 100, 200. You might get 200. You're switching 200 times as much current through the collector to emitter. So this is kind of the power side of the transistor, and this is the switch side of the transistor. So in this case, when you provide a signal here that allows a path to ground, I hope you see that. If this is our positive supply and this is ground or negative supply, when the transistor is off, there's no current flowing through here, but when it's on, then current can flow. So if you see, NPN sounds kind of a lot like syncing, and those are used somewhat interchangeably by manufacturers. They may list a sensor as an NPN type, and that means that it's going to switch the ground. The opposite type of transistor is called a PNP. And again, it's double diodes. Now the arrow points inwards. This is still the base, but this is the emitter now. We've flipped it this way, and now our load's always on the collector, but now our collector is on the bottom and our voltage source is on the top, and our base is our switch again. So again, it could have the switching information that's deciding whether it should be on or off is coming out here, and then the transistor is the final actual switch, and in this case our output would be right here. So this would be the output to the PLC. In this case, when the transistor switches on and allows current to flow, you can see that now the voltage will be high here. So this is going to provide a positive output, whereas this was connecting to ground. This was allowing current to flow through the output, in the output to ground. Now we're allowing current to flow out the output to whatever our load is out here. So this is PNP, which is our equivalent to our sourcing. Okay, I think that's probably enough of the background of what NPN and PNP mean. They're basically the opposite types of transistors. One, the load is on the collector with collector tied to positive. On the opposite, on a PNP, again, the load's still on the collector, but now it's tied, the load's connected to ground instead of positive. So they're just inverse. Again, you don't need to memorize this stuff, but you need to have some sense of the idea of what PNP means, what NPN means. So if I'm using an NPN transistor, what we would call syncing, then I need to make sure that my PLC card is sourcing type, and vice versa. If my sensor is a PNP type or sourcing, then my PLC input card needs to be syncing, right? The PLC needs to have a negative that the input device is providing a positive to. So if we had a PNP sensor, that means the PLC, if this is the output going to our PLC, the PLC better have the common for the input. How can I write that? If this is input 0 that we're connecting to, then the common for input 0 better be tied to ground, right? We're switching the positive side, so the PLC needs to be grounded. So that if the PLC is providing the negative, then the PLC is syncing, right? So you can see that we're pairing a sourcing sensor with a syncing input card. And the opposite would be true. If we had a syncing NPN sensor, then our card better be sourcing, which means that the positive power supply would be tied to the common. Okay, let's think about when applications beyond just input. So we've now shown we can use these active input devices, proximity sensors based on inductive principles. There's capacitive sensors. There's photo eyes like you used in MEC232. So that's all about the input world. This same principle applies to outputs. When we went through syncing and sourcing for outputs, we were looking at it as if it was just a independent device out there, right? We would have a PLC, let's have a PLC output card. So just note, I'm changing to output, back to outputs now to talk about that. If we have a PLC, let's say it's a sourcing PLC output card. So let's say this is output 0. If it's a sourcing output card, that means the PLC is going to be providing a positive, right? And then our device, before we were looking at, like if let's say it was a lamp or something, our lamp would always have a ground and the PLC would be switching the positive. So this is output 0 and the common would be connected to positive, and then the PLC internally has its own transistor that when we engage it, it puts out positive on output 0, which flows through the lamp to negative. This would be our positive supply. This is our 24 volt DC supply. Okay, doing this here. Okay, so that's the simple way we did of a sourcing output. This is PLC sourcing. But now let's think about, there are definitely conditions, like I showed right with early on we started talking about this, that my output is not just turning on a lamp. It's being used as the input for another electronic device. So this is one of those times where it's key, it's critical to make sure that you're matching your PLC output type with your device input type. So in this case, these are sourcing outputs. So then we have to be using syncing inputs on our stepper drive. And if you look at the side of our stepper drive, you'll see that the labels for each input, for pulses, direction, and enable, they have both a positive and a negative. And that's nice because what that allows us to do, two different things. You can either have differential signals, which we'll talk about in a future lesson, or it also allows you to use single-ended signals, but as either positive or negative signaling. So either PNP or NPN kind of. And if that's true, then you're going to either tie the one you're not using to high, or you're going to ground it. So again, that doesn't have to all make sense yet, but you need to understand why we have to get the manual for whatever device we're connecting to verify that our output type from the PLC matches the input type of whatever we're connecting to. Okay, so let's do an example problem to try to show you how you would determine the correct way to connect a couple different types of inputs and an output to the PLC that we're going to be using in this class. So let's start out by just kind of coming up with some parts we're going to use. So let's, like I said, let's use the PLC we're actually using in this class. So that is a 2080 LC50 24 QBB. So we'll need to look up the user manual for that to get some information about the I/O, and then let's use this proximity sensor for one of the devices. So let's use that as APS 4-12M E2, and it looks like there's a D. So we'll look up that one. So we'll use that as one input, and we'll need to figure out, is that syncing, sourcing, whatnot. Let's also use, let's say we're going to have one normally open push button as an input. That's fine. And then for outputs, let's have one control relay and one lamp. Those are both outputs, and they're both 24 volt DC. In another week's assignment, I'll have you go beyond this. So these are both pretty simple outputs, right? They're discrete components. They're not active. You just run power through a control relay coil. You don't have to figure out, whether it's a syncing or sourcing PNP device. A control relay can be used with either a syncing or a sourcing output. Same with a lamp, right? All it needs is a power and a ground. You can switch either one of them, and that will work. Okay, so let's start by looking at the input and output specifications for this part number here. So I've already opened the user manual, and let's scroll down to the table of contents, and we're going to look under, wiring your controller. Okay, and actually before I do that, I'm going to skip to the specifications to just see what I can find out about type of inputs and outputs in this processor. So it's a micro 850 24-point controller. So QBB is this last one over here on the right. So looking at the types of information it gives me, input circuit type is 12 to 24 volt sync or source, and these are the standard inputs. And then there's a couple inputs that can be high speed. We're not worrying about that right now, but they too can be either sync or source. So it looks like our inputs, we have some flexibility. We can choose whether they're sync or source. Our output type looks like these first two models. If you're looking across the top, right, we have 4 models here. The one we're interested in is the last one. The first two are relay. The second one are DC syncing outputs. And the last one, the one we're using, is a DC source. So it looks like all our outputs have to be source. So that's information. Let's come back to here. So we know that these can be either syncing or source. Both of these, we have flexibility about that. For our outputs, we're set on them being sourcing, because that's the type of controller we have. So if we knew that we needed to connect to some type of output devices that had to use a syncing PLC card, then we would have to look at changing our processor to be this QVB instead of QBB. You can see that's the only distinction between those two, is whether the outputs are syncing or sourcing. Okay, so let's stay in the user manual and go back up to the table of contents and go to that wiring your controller section, where it'll actually show me the terminal blocks, so I can kind of sketch out what I'm going to connect where. Okay, control wiring diagrams. Let's start there. So starts out, this is the same user manual for 830, 850, and 870. So we're in the 830 series. So we'll scroll down until we find our part number, which was 2080 LC50. So not these ones. QWB, not those ones. AWB, not those ones. Okay. Here we go. 2080. So those are 2080 LC50 24 QBB. That looks like it to me, right? Okay. So these two diagrams right here. Let me zoom out just a little so we can see them both at the same time. This upper one, these are the physical layout of the blocks. And then down below, they give you some examples of how you can actually connect devices to that. So before we start drawing, let's just kind of review what we have here. Looking at this block, it looks like the first 8 inputs all share a common. And then the last 1, 2, 3, 4, 5, 6. Last 6 inputs also share a common. So if we then look at those commons to get a sense of whether we're syncing or sourcing, you'll see that it lists 2 different things we could connect there. If we're going to use our card as a sourcing card, then we're going to hook the positive up to the common. And that sounds right from what we've been talking about, right? If the PLC is sourcing, we're going to bring power to the common, and then the PLC is going to switch that power. Actually, that's backwards, I guess how I'm saying it. Since we're looking at inputs, the PLC is going to, if it's sourcing card, the PLC is going to have a positive available at each terminal through the common, and then the input device will determine whether current flows out of that PLC source to the ground. So if it's a sourcing input card, the positive is tied to the common. If instead we want to use it as a syncing input card, then we would tie our negative of our power supply to the common. In that case, power would be coming to all of the input devices. They'd switch power, which would then sync into the PLC and out the common to the ground rail. Okay, so we said we could use either syncing or sourcing. And just to make things interesting, let's say that we're going to do one of each. So we'll do, let's say we're going to use syncing inputs on our first 8, and we'll do a sourcing input on our out of this second group of 6. So if we come back here, let's start that. So let's say we're going to use, well, let's say we actually need to, sorry, get the camera up there. Where's the right screen? There we go. Okay. So the push button, it can be either syncing or sourcing, right? By hardware, it doesn't matter. This proximity sensor, that's not the case. It is either a syncing or sourcing sensor. So we would need to check the schematic for that. We already saw the little version of the schematic here, but just for your reference sake, because I'm going to give you an assignment to do something just like this, I'm going to show you the website where you could get that information. So I purchased that sensor from a company called Automation Direct. So let's look. I think I have their web page up on one of these. Yeah, so let's duplicate that. Go to the home page. So this is a great source of any kinds of sensors, cheap PLCs, all kinds of stuff. I encourage you to look around this site if you ever need to. But we were looking at an inductive proximity sensor. Let's see what it comes up with. So I'm going to look under sensors. And you can see that that style that I chose was this rectangular one here, and it's that one there. And then looking through, you can see there's on the left side there's different options to narrow it down. So the part number I was looking at is APS 4, which that means it's a 4mm sensing. Actually, I can just type it in here to make it easier for you. APS 4-12 12M, and you can see it's filtering them down as I'm typing, -E2, and then there's only one option left, so we can click on that. And then if I go to the page of it, it has a lot of information, but specifically what I'm looking for are the technical specifications again. So let's open those up. That's what I already had open. And if we look at it here, this is one data sheet for kind of the family of sensors. And so again, I would look up my part number, APS4 12M. So I felt like I was getting close here, but then it's a 12S. So that means I need to come down here, APS4 12M. And you can see the difference there is whether it's sensing out of the top of the sensor or the front of the sensor. So this is a front sensor, 12M E2D. So reading this chart tells me how much it costs, how far away it can sense an object, how it mounts, and then here it tells me is it normally closed, normally open. So that tells me is that, and that refers to is it provide a voltage when there is a device sensed or when it's not sensed. So mine's 12M E2, so that's normally open. That means it won't pass a current unless it senses a part. And then it tells me it's PNP. So that's what I came to this site to try to find out. What type of configuration is this sensor? And then if we continue on, you'll see that for wiring, it refers me to diagram 2. And that's referring to right down here. And if I zoom in on that, you'll see that's just another version of the diagram that was on this tag right here. But that's how you find them for when I give you a different part number to use. So let's look at this diagram now. Diagram 2. It looks like in this case, this box, which represents the load, it is always tied to the negative and the sensor is providing a positive. So in my mind, the way I'm teaching you to think of these configurations, that means this sensor is a sourcing sensor. It is providing a positive current flow, and the PLC is providing the ground path, right? So the PLC would need to have a syncing card in that case. The common of the PLC should be tied to ground. So we can go back to our diagram and say that it is a PNP, so that means sourcing. It's providing a positive, right, to the PLC. So I said I wanted to do one of each. So if this is a sourcing device, that means that the PLC should be syncing. So if we're using our proximity sensor on a syncing PLC input, let's connect up our push button as sourcing from the PLC's perspective. So just let's put that down here as PLC sourcing, but the push button will be syncing. Okay, and we're tied into both of our outputs being sourcing because that's all the hardware can support. Okay, so let's go back and look at our manual. Let's see, do I have that one still up here? That's the wrong one. So here again is our terminal blocks. So we're going to use one syncing and one sourcing input, and it looks like, looking at this, either group can be either way. So let's just start out by saying that we're going to do our PLC set up for the proximity sensor on input 0, 0. So that's terminal 2. So I'm going to draw on my, let's see if I can shrink this down a little. See if we can get to where you can see both my paper and card. You can see most of it there. Okay, so on our input block, I'm not going to draw the whole thing. I'll just kind of I didn't give myself enough space there. Sorry. So I'm only going to draw the terminals we're actually going to use. So we're going to use terminal 1 and we're going to use terminal 2. And then we're not going to use anything again until terminal 10, it looks like, is the next common. So we'll use terminal 10 and terminal 11. Okay, and we said we want to use our proximity sensor as our syncing. The PLC will be syncing. So for our common 1 then, if it's syncing, then terminal 1 is going to hook to our DC 24 volt negative, connect to terminal 1. I'm just going to draw a DC power supply over here, and we'll say this is negative, and we'll have a plus over here. Okay, so we have our proximity sensor out here. It has 3 wires coming to it. And if we go back, or I'll just do it with this one right here, you can see, I'll hold it up there so you can see it closer a minute, that brown is connected to, there, that makes it clear. Brown is our positive supply, blue is our negative supply for power, and black is our signal output. So let's deal with the 2 easy ones first. So brown is going to tie to our positive 24 volt DC. So this is our brown. And blue is going to tie to the negative. So I will bring up here. This is blue. And then black is our output. And we'll tie it into terminal 2. And let's verify that it matches what we would expect here. This shows our PLC device, represented by the box, having black coming in as a signal, and then the common tied to ground. And looking here, that's what we have. So basically that black box right there that's shown as the PLC is basically right in there, right? Terminal 2, terminal 1. That is the sensing element in the PLC. Okay, so we've got our proximity sensor set up. It is a PNP sensor, so it's a source. So our card is set up syncing, meaning the negative is tied to the common. Now let's do our push button that we want to set up with the PLC as sourcing. So if the PLC is sourcing, that means the common is going to be tied to the positive 24 volts. So I'll bring it up here, tie to the 24, and I'll just label it DC 24 volt positive. Okay, and then so the PLC is sourcing, so that means the input device is syncing or providing a path to ground. So if we're thinking about it from a current flow perspective, we have positive current coming to the common. It's being sensed internally, and only if we press our push button will we provide a path to ground. So this is our minus DC. So this is the PLC is sourcing, so the input switch is syncing. So we've now set up one input as sourcing and one input is syncing. So we're halfway there. So now let's look at our outputs. And for a minute, let's maximize this a little bit. So our outputs, we said they have to be sourcing. So that means the common of the output cards is going to be tied to positive. And you can see that they're only listing positive. You'll also remember that it talked about a high speed outputs, high speed, that some were higher speed. And so you can see they're grouped here into, let's see, the first 4 inputs, input 0 through, actually just the first 2, I'm sorry. Input 0 and input 1 share a common. And inputs 2 through 9 share a different common. Okay, so you can also see that they have the positive tied to the common, but they're also providing a negative for the common rail as well. But the actual switching is happening from the positive side here because it's a sourcing. So looks like we have 2 outputs. They're both going to be sourcing, so we can just use them both as input 0 and input 1. Okay, so that's terminal 4. Now 3 is the common, 4 is input or output 0, and 5 is output 1. So I'm going to bring 24 volt DC, and again that could be from the same supply. Oh, sorry, you can't see my drawing here. Okay, so I'll bring, I'm just going to use a separate power supply to make it so I'm not drawing so far. So here I have another positive and minus 24 VDC, and we're sourcing through our card, so that means I'm going to bring positive to the common. Then the PLC internally will switch that positive supply either on or off to each terminal. So let's say for terminal, let's bring my negative supply. So for terminal 4, I'm going to have a control relay coil. And for terminal 5, I'm going to have a lamp. So let's say it's a green lamp. Okay, so it's a very basic kind of I/O wiring. We only have 2 inputs and 2 outputs, but I think that's enough for today as far as new learning. So I hope that all made sense, how we determine what type of sensor we're using. If it's a sourcing sensor, we use a syncing input. Vice versa, if it's a syncing input device, we use a sourcing input card. PNP is usually mean the same thing as sourcing, but always find the data sheet and verify that. So now I'm going to give you an assignment to do where I want you to do something just like this. So let me get you the part numbers. Okay, so for the last part of the assignment today, I want you to create your own version of what we just did here. So I'm going to give you some input and output specifications, and I want you to create a basic input and output diagram like this. Try to keep your drawing as neat as possible. Label your terminals as far as if they're positive DC voltage, negative DC, if they're the signal, that kind of thing. Make sure I can kind of understand what your goal was. So if the wires had colors to determine what they are, write the color on them. If they have a function, write that along it. Like here, I should probably write along here input 0. This one, I can't remember without looking at it, it's like maybe input 8 or something. This would be output 1. This is out 2. Okay, think you get the idea. So here's the part numbers I want you to do. I want you to use a 2080 LC30, so an 830 series, 24 QVB. That's the PLC that you're using. So find the user's manual for that and get to the wiring diagram. This is actually the same user's manual as the 850 that we're using, but this is a different part number, so it'll be a different wiring diagram. That's the processor. As far as inputs, I'm going to have 3 inputs I want you to wire. The first one, I want to be a normally open push button. I don't care if it's syncing or sourcing. You can figure out what you want to do there. The second input is going to be a proximity sensor from Automation Direct. So go to their website, and the part number for this proximity sensor is AE1-AN-2A. And you'll need to figure out if that's a syncing or sourcing sensor, PNP, NPN, etc. The third and final input is also Automation Direct. This time it's a photo eye, and the part number is QMRN-0P-0A. And again, you need to go figure out if that's syncing or sourcing and connect it appropriately. Hopefully it's of a type that will work with this processor. And okay, so now outputs. I want you to connect. Output 1 should be a control relay coil. And output, let's say output 9 should be a red lamp. And again, you'll need to figure out if there's limitations in the processor, whether it can be syncing or sourcing. If you have the choice, I don't care which one you do, but I don't think you have a choice on that processor. Okay, lastly, I want you to show the power connections, what terminals power connects to on that PLC, and what, so tell me the terminals, well, show them on your diagram connected to the right terminal numbers, and label what voltage they are. I.e., is it 12 volts DC, 60 volts AC, etc. Okay, that's it for this lesson. So I've given you a number of different assignments throughout the videos. I want you to collect them all onto ideally one page. It can be up to 2 pages because if this drawing takes up space. But just get everything written out, answers to each questions where I had you spec or find out information for me, and then scan or take photos of them and upload those for your submission for this assignment. Whew, that's a long lesson today. I hope this made sense. Go back and rewatch things that didn't. Send me emails. I'm happy to help work through this. Don't feel bad if it doesn't make sense the first time. It is a confusing concept, and like I said, manufacturers don't make it easier by this vagueness in whether they're referring to the input device or the input card of the PLC when they say syncing or sourcing. So biggest takeaway from this lesson, memorize this. Anytime you're connecting an input, make sure you have the data sheet for both the sensor device you're connecting and the PLC you're connecting it to. Okay, good luck. Let me know if you have questions.